Okay, now here's one more look at the combined gas law. But if you take a look at this, you'll notice that there's one variable that we've talked about that is not included in the combined gas law, and that is the amount of gas, or N, which represents moles. A lot of times the combined gas law does not include moles, and there's a reason for that. Very rarely are you dealing with a situation in which the amount of gas is changing. Usually we assume that the amount of gas inside the container is staying constant. Okay, so we don't often deal with N as a part of this equation, because if any part of it is remaining constant, it doesn't have to be a part of the equation. However, there are situations in which the amount of gas could be changing. You could be doing an experiment in which gas is being added to a container, or you could have a gas leak, say, for example, in your tires. Okay, so we do need to kind of take a look at where the amount of gas fits into all of this. So I want you to just kind of think about how we've set the equation up to this point in terms of either being directly proportional or inversely proportional. Now I want you to think about moles of a gas. If the moles of the gas go down, what do you think is going to happen to the pressure? Knowing that, where do you think moles of a gas would fit in this equation? So let's take a look at the combined gas law when we take moles into account. Here's the combined gas law when we take moles into account. So if you guessed that moles of a gas would fit here in the denominator, you are correct. If moles of a gas goes down, the pressure goes down, which means they're directly proportional. So we would set it up like this. So this is another form of the combined gas law that takes moles into account. Like I said before, it's not commonly used because a lot of times the amount of gas is not changing, but if it were, this is how you would set it up.